Well, then what's going to happen, right? If you make if you make the denominator of a fraction bigger, the whole fraction gets smaller. So if you let that denominator blow up to infinity, then the whole fraction basically collapses to 0. And it doesn't matter if the infinity is positive or negative, it's still just 0, because remember, 0 is neutral. It's not positive or negative. So really understanding how this stuff all works out is going to be very, very useful, because a little bit further down the line in the unit, we're not only going to be evaluating expressions that started as rational expressions, we're actually going to be stacking two things on top of each other and creating a rational expression. So you really need to make sure you understand how to read your result. So this is a good recap of how to deal with L'Hopital. So what I want to look at now is an example of a limit that's pretty famous that is going to use L'Hopital in finding the result. So when we actually want to find the limits of sequences. All right, so let's look at an example. So we have a sub n equals 1 plus 1 over n, all raised to the n. So this is actually a really famous limit. I know the answer before we even start, and some of you may have already recognized it. But we're actually going to get, when we work this problem out, we're going to get that the limit of this sequence is e to the 1, right? Don't fall in the trap of just assuming it's e, because when we're done with this example, I'm actually going to show you how we can tweak this to change its value. So what you're really supposed to get out of this is that this is e to the 1, all right? Now, I'm going to show you the proof of this. Later on in the section, I'm actually going to show you a handful of limits that are in your textbook that if you recognize them, you're allowed to just state the result. I don't have to see you prove them back from first principles. I do want to show you, though, where e comes from, because a lot of the intermediary steps of the proof are really good algebra moves that you need to know, and this limit does involve L'Hopital. We actually need L'Hopital to prove this is true. So if we set up the limit, right, when we're finding the limit of a sequence, we always take the limit to infinity. And I want to evaluate this limit. So a seemingly logical chain of thought that is incorrect would be to look at this limit. If we only look at what's inside the parentheses, right, we would see, well, 1 just stays 1, but we know 1 over n goes to 0. We just saw that in our L'Hopital example. So some people might say, well, the whole inside of this is just 1. Well, if I raise 1 to the n, and n's going to infinity, 1 times 1 times 1 times 1 all the way up to infinity would just be 1. So a very common incorrect answer to this would be that this is going to 1, and it's not going to 1, it's going to e. So how do we show that that's true? So in order to evaluate this limit, I need to get that n out of the exponent, and there's only one algebra move that allows us to remove a variable from an exponent, and that is to involve logs, right? So I can take the log of this expression, or the natural log, but if I do, I need to also do that to the other side of the equation. And I don't really have another side to this equation. So let's assume for a minute that the limit exists. I mean, we know it does, but let's say we didn't know, right? The limit exists, so we're just going to call it L. And so the name of the game is, what is L? Well, now that I've created another side to this equation, I can actually take the natural log of both sides. So we're going to take the natural log of the expression on the left, and then similarly, we're going to take the natural log of the number on the right. So for the rest of this problem, what I'm going to do is I'm just going to kind of set this aside, and we're just going to look at this side of the equation, and we're going to simplify it all the way down till we can't do it anymore. Once we've got this simplified as far as we can go, we'll set it equal to this, and then we'll solve for L. So the first step in my algebra is going to be to move that n out of the exponent. That was the whole reason we did this to begin with. So I'm now going to have the limit as n goes to infinity of n times 1 plus 1 over n. Well, I kind of mentioned that L'Hopital was going to come into the equation, and in order to use L'Hopital, I need a ratio. This guy doesn't really count. I need an expression with n over another expression with n. So let's think about this n right here as n over 1. Okay, we usually, we don't put 1s in the denominators because they're not really necessary. So if you wanted to divide a fraction by a fraction, the first thing you would do is you would multiply by its reciprocal. So if I look at this expression, I'm like, oh, well, somebody's already done that. I want to undo it so I can go back and look at the original fraction. So the opposite of multiplication is division. So if you divide by the reciprocal, you've now gone back an algebra step. So this is equivalent to saying the limit as n goes to infinity of 1 plus 1 over n over 1 over n. And I realized here, I forgot I still have a natural log. My bad, guys. All right, because we still got that natural log. So now when I look at this expression, I have a ratio, just like I wanted. And let's look at the limit of the numerator and the denominator. So remember, n's going to infinity. So if we look inside this log function, we see that the expression inside the log is just going to 1, because this is going to go to 0. So the natural log of 1 is 0, so I definitely have 0 in the numerator. And we can see 1 over n is going to go to 0 as n goes to infinity. So we're in a 0 over 0 situation. That means I can take the derivative. So the derivative of the numerator, right, we're doing this separate from the denominator. The derivative of the outside function is just 1 over u. So I'm going to get 1 over 1 plus 1 over n. Then, because of the chain rule, I need to multiply that by the derivative of the inside function. And the derivative of 1 over n is negative 1 over n squared. The derivative of the denominator is also negative 1 over n squared, because we just took the derivative of 1 over n. And you can kind of do that in your head if you remember that 1 over n is n to the negative 1. And then you just use the power rule. Negative 1 times n to the negative 2, right? So this canceled, my negative 1 over n squared cancels negative 1 over n squared. So now I just have to take the limit as n goes to infinity of 1 over 1 plus 1 over n. And we can see the numerator is 1, the denominator is also going to be 1, so this limit just equals 1. So I would say we did a pretty good job. We've got this about as simplified as you can go. You can't get simpler than 1. So remember, right, this was the original expression. All we've done was look at the left side. So now I can say, well, 1 equals natural log of the limit. So if I want to solve this for L, well, you get the L out of the natural log by raising both sides over its own base. So if I raise both sides over e, I get that e to the 1 equals L, just as desired. So there's actually a general form of this limit, right? Because remember I said up here, don't fall into the trap that this is always going to be e, right? So we could have made a slight adjustment to this formula. So now what we can say is the limit as n goes to infinity of 1 plus x over n raised to the n equals e to the x. So in our original expression, this number was a 1. It was this number right here that told me what to put in the exponent of x. So if you went back and redid this proof and changed this number to a 2, you would see you come out with e squared, right? And this is true for any x. So it could be positive, negative. The one thing that's a little strange for you guys to see is like we've got x's and n's mixed in the same expression. X is not a variable here. X is actually a constant. N is the variable. So if I said a sub n is now the expression 1 plus 3 over n raised to the n, well, you can simply say directly that this converges to e cubed. And I knew it was e cubed because of this number right here. So you won't ever have to show me all of those intermediate steps again, but it's good to kind of see where things come from, and you should recognize this limit if it comes up again.